The Claisen condensation is really similar to the aldol addition condensation reaction. The main difference is that it uses an ester instead of using an aldehyde. The conditions of the reaction are also different. First of all, it's a two-step process, as you can see, and I'll explain that when I draw the mechanism. Second of all, it uses a slightly different base. Instead of using OH-, which we use for the aldol reactions, we use OR- and alkoxide. I do want to make a note here that when you're doing this reaction, the OR group of the ester must match perfectly with the OR- group, the alkoxide, that you are using as the base in this reaction. If you don't match the OR groups with each other, there is definitely a possibility that you'll get some unwanted byproduct over here. The OR groups, in addition to doing the Claisen condensation reaction, they're also going to be swapping each other out like constantly during this reaction. And so you want to make sure that if the OR groups are swapping each other out, it doesn't actually make a difference. Like if these are both OET groups, it doesn't matter if they swap each other out, we're going to end up with OET here in the end. Let's draw the mechanism of this reaction. I'm going to use a pretty simple ester for the mechanism. And because I'm using a methyl ester, I've got an OCH3 group here. That means that the base that I want to use for this reaction is methoxide, OCH3-. Again, that's because I need to match my base with the OR group of the ester. In the first step of this reaction, just like the aldol reaction, our base is going to grab one of the alpha hydrogen and put the electrons from that carbon-hydrogen bond onto the alpha carbon, so it's going to have a lone pair. So it will look like this. And in fact, just to save space, I'm not going to draw that second alpha hydrogen anymore. We know that it's there. We're just going to draw that. Now this enolate is going to add itself, react with a second ester. So I'm going to draw in ester number 2. It could be the exact same ester or it could be a different ester if we're doing like a crossed reaction. The negative charge on the alpha carbon is going to go after the carbonyl carbon of ester number 2, and it's going to open up that carbon-oxygen bond. And this is where we want to be really careful when we're drawing the next intermediate here. We want to be super careful that we get all of the carbon atoms connected in the right order. So I'm going to number all of the carbon atoms. And if you watched my video on the aldol reaction, you know that my recommendation is that you give every single carbon atom its own number. So I'm not repeating any of the numbers. I've got 8 carbon atoms here that I need to account for all together in this reaction. Also, I like to start by drawing the ester that is getting attacked first. So over here when I'm drawing my intermediate, I'm going to start by drawing this ester, and that is carbons 5 and 6 and 7, and then the oxygen and carbon 8. And my carbon-oxygen double bond is now a single bond with a lone pair on the oxygen. So here's carbons 5 and 6 and 7 and 8. And in this reaction, I created a bond between 7 and 2. So I want to draw next, I want to draw my bond from carbon number 7 to carbon number 2. And then I want to look at what is attached to carbon number 2. Carbon number 2 has carbon number 1 attached to it, and carbon number 2 also has 3 attached to it. I'm going to draw carbon number 3 right here. Carbon number 3 is part of the carbonyl group, so we'll draw the carbonyl group in. And then from carbon number 3, we have our OCH3 group, OCH3, and that is carbon number 4. In the next step, we're going to bring the lone pair of electrons back down to remake the carbon-oxygen double bond, and we're going to get rid of this methoxide group, the oxygen, and carbon number 8. And I'm going to draw that guy over here. So when I draw this next product here, next intermediate, I'm going to do my best to draw this molecule exactly the same way. Again, I'm really trying hard to minimize the chances of me losing a carbon or connecting anything in the wrong spot. So even though this drawing looks really funny in the way that I've drawn it, I think I'm going to put my numbers back in. I think I've got everything in the right spot. Again, I can't emphasize enough how easy it is to actually lose carbon atoms or connect them in the wrong spot. So as you're drawing these mechanisms, don't worry a lot about making the structures look pretty. You can make them look good when you're all done drawing. In the middle parts, you just want them to be right. So I've drawn this correctly. It looks good, and I have don't forget I have this leaving group, this OCH3 minus, which I'm actually going to write over here because we're going to be using it in the next step. So this strong base that we produced, the leaving group, the OCH3 minus, because it's a really strong base, even though this is like really what the product is that we would like to be making, that strong base is going to go after the alpha hydrogen that is on carbon number 2. So I'm going to move that little 2 and I'm going to draw this hydrogen right here. This alpha hydrogen is in between 2 carbonyl groups. So it's really acidic, really easily lost. And this strong base that we removed in the previous step is going to go after that alpha hydrogen. Even though we definitely don't want it to, we can't keep it from happening. So we're getting another deprotonation here, even though it's not what we want. 5, 6, 7. And in this step, I'm going to work on making my structure look a little bit nicer. 5, 6, 7 goes to carbon number 2. Carbon number 2 has carbon number 1 hanging off down here. And then we go to carbon 3 right there. Carbon number 3 is part of another carbonyl group, an oxygen, and a methyl group. And then don't forget we've got a negative charge on that carbon number 2 right there. And again, this is not the product that we're trying to make. It's just been unintentionally deprotonated by the methoxide. So this is why we need step number 2 with H3O+. That second step with the H3O+, we're going to put that proton back onto carbon number 2 so that we end up with the product that we actually want. And it's going to look like this.